Started?
Sure.
All right. So, hey everyone, thank you for coming back to the IIF distinguished lecture offered by Professor Rob Hyndman. Today is the second lecture. I believe Pam already sent you the link recording for the first one. So today Rob will continue his lecture on hierarchical forecasting. Rob, please.
Thank you, Tao. Let me just move some stuff off my screen here. Okay, so hopefully you can see my slides. So we're going to continue with the themes that we started earlier in the week. So remember, there's 4 of these lectures that are building sequentially and trying to introduce the main ideas behind forecast reconciliation. So last time we introduced the concept, and I showed you, one of the main results, which is the minimum trace estimator. And today we're going to continue talking about point forecasts in a reconciliation setting. And I'm going to touch on a lot of other papers that have contributed to this literature and sort of highlight some of the key ideas. So just a quick recap. So the idea is we have a collection of time series that are related, usually due to aggregation, but maybe some other type of constraint. So the example on the left there is the tourism data that I showed you earlier in the week, where we have total tourist numbers for the whole country and then split them by state and then split them by some other geographical areas like zones and regions. And we want the forecasts for all of the different levels, and we want them to add up appropriately. So the concept of forecast reconciliation is you do all the forecasting for all of the different levels, and then as a second step, you adjust the forecast to make sure that they obey the constraints. So you would forecast at all the regional level and then all the state level and then the national level. Those forecasts won't add up because you've used different models, but then you do this adjustment step to make sure that the forecasts are moved around just enough to make them add up. And so we talked about that last time, and I talked about the minimum trace reconciliation, which is the optimal way to do this. And what we're going to do today is to discuss some other ways of doing it, and in particular, some of the properties of minimum trace reconciliation. Okay, but before I do that, I just wanted to say one more thing about the historical background to this, and that is that the concept of reconciliation in time series started long before forecast reconciliation. In fact, it goes back to the 1940s, where there was a paper on reconciling national economic accounts. The first author there is being Stone. And that was the idea where there was national economic accounts where you have measurements of production and income and capital and outlay and so on. And they're meant to add up appropriately, but they don't usually do that because there's measurement error. And so one of the jobs of official statisticians is to sort of try to adjust these things. And Stone and his co-authors came up with this way of doing it, which turns out to be equivalent to what we're doing with forecast reconciliation. They're not forecasts, though, they're data. And then in the 1970s, Byron extended that work, showing how to do it more computationally efficiently. And this was quite a big deal. Stone won the Nobel Prize in Economics for coming up with this idea. And we're really using the same idea in forecasting. But George and I didn't know about Stone's work when we were first developing this. The same approach is actually also used for reconciling seasonally adjusted data. So you might do you might have some employment numbers and you want seasonally adjusted employment, and you want it for the country, but you also want it for states. And while the data add up appropriately by definition, the seasonally adjusted series often don't, and so you need to reconcile them to make sure they add up. And so again, official statisticians have been doing this for some time. And then there's other work being done on temporal reconciliation. That is where you want your data over monthly level to add up to the data over quarterly level or annual level. And there's some work being done on that back in the 1970s by Chow and Lin. and then doing it in both directions, for, reconciling time series that are related to each other, but also you want them to reconcile across time. So that's cross-temporal reconciliation. And Tommy DeFonso was the first, I think, to do that in the early 1990s. An interesting story here. So I'd never heard of this work when we first came up with the idea of forecast reconciliation. And Tommy read the first of our papers on the topic and realized that it was the same idea that he had been using in time series reconciliation. And he then went on to make some contributions to the forecast literature as well, which we'll talk about some of those today. Okay. So let me just talk a little bit about the notation again to remind you. So remember we have, and I'm going to use this little example here at the top quite a bit today, just to, because it's small enough that we can write down the matrices and see what's going on. So we have 4 series. We have 3 bottom level series, which I'll call A, B, and C, and we have a top level series, which I'll call total, and A, B, and C must add up to the total. So the 4 series overall, we can write in this vector Y. The bottom level series we write in this vector B, and then the summing matrix shows how you add them up. So the 3 ones adds up the 3 bottom level series, and then the rest of the matrix is just an identity. So that's the notation that we introduced, and you know, I'll keep using it. So remember the Y is all the series, the S is the summing matrix, and the B is the bottom level series. The forecasts we call Y hat, the original forecast. They're the forecasts of all of the series, ignoring any constraints, so they won't generally add up appropriately. And then the reconciled forecasts are the ones that will add up, can be obtained using this equation here. Y tilde is equal to the summing matrix times some matrix G, which we have to determine, times the base forecasts. And then the optimal solution is obtained when G is given by this expression here. Okay, so that's sort of the main theoretical results we covered last time. Let me now introduce a slightly different notation. So over on the left here, I've got the same thing that you saw on the previous slide. Y is equal to S times B. Here is the Y, the S, and the B. And we're going to separate it into the series that are aggregated and the series that are at the bottom level. So the series that are aggregated are in this sort of yellowy color, and the series at the bottom level are in red. And so we can write the whole thing by splitting the big matrix into the aggregated series, A sub T, and the bottom level series, B sub T. And the S matrix can also be split into a part at the top, which is aggregation, and a part at the bottom, which is just the identity. Another way to write this is to use a constraint matrix. So if I write the matrix C as C times Y, and that has to equal 0, then that C matrix is simply a 1 followed by lots of minus 1s. And more generally, it's an identity for the top level series, the aggregated series, minus this matrix from over here, this aggregation matrix. And that's it gives exactly the same result, but it's a more efficient way to write it because you're not having such big matrices. This, in fact, is only 1 row, whereas the summing matrix is 4 rows. That doesn't seem like much, but when we talk about millions of series, that's going to be a considerable saving. Okay, so in general, we can write, not just for that little example, but for any of these types of problems, we can write Y is equal to the aggregated series at the top and the bottom level series at the bottom. So the aggregated matrix and identity, and then the constraint matrix can be written as C times Y equals 0. So this is more general, it's more parsimonious, and we can write down the equations and handle them more computationally efficiently. The other thing I should point out is that although all of my examples involve summing things, and so the summing matrix, the S matrix, and the always involves 0s and 1s, and therefore the C matrix generally involves 1s and minus 1s and 0s. They could actually contain any real values. There's no reason that they should all be zeros and ones. They can be anything. So this approach to forecast reconciliation was pointed out by Tommy DeFonso and his PhD student, Daniela Girolamo, and a paper that's going to come out in the IIF, but the notation goes back a lot. The idea of a constraint matrix goes back decades. It was just that they pointed it out that this was a more efficient way to do it. Assuming C is full rank, then we can write down the optimal solution using this equation here. The M matrix, which is the matrix you map, so the M for mapping, and it's taking the Y hat and turning it into Y tilde, taking the base forecast and turning them into reconciled forecasts. That matrix can be written in this form here. And that was the approach derived by Byron for reconciling data. And we rediscovered it and published it in our paper, the one that appeared in JASA. And Tommy and Daniela basically said, well, you can use this all the time instead of using the summing matrix, which we hadn't actually realized when we wrote that JASA paper. So this is more efficient than this approach, the bottom equation, which is the one that I showed you last lecture earlier in the week. And we're going to use both of these notations. Sometimes this one because it's in some ways a little easier to understand, depending on the context, and sometimes the top one because it's more efficient. So I just wanted to also do a numerical example of what this looks like, because I think it really helps understand what's going on. So again, we'll take this little example where I've got 4 series, and therefore the aggregation is just a lot of ones. So it looks like this. And the S matrix looks like so, and then the C matrix looks like 1, -1, -1, -1. And then if I try to just derive or compute the mapping matrix, so I take this equation and I just plug in the various bits. So it's an identity at the front. I'm going to set the covariance matrix to the identity just to keep things simple. And then I take the C matrix, transpose it. This bit in the middle here, this little section here, is going to be CC prime. And so that's just going to be going to look like this. That's going to be 1/4 because you're going to be taking the sum of the squares of these things and then inverting it. Okay, so we do that, write it out, and come down to what we've got at the bottom. And so this is telling us that the reconciled top level series, the total, is going to be 3/4 of the original total plus 1/4 of each of the original base forecasts. And you can see that that makes sense because the total is meant to be the sum of the bottom ones. So if you take 3/4 from the total, then you've got the 1/4 left for each of the subtotals. And then the second one, the A series, is going to be 3/4 of the original A series. And then you want to use the rest of the series to sort of get another estimate of A. Well, the rest of the series are the total and B and C. So the total minus B minus C gives you the A series back. And so you end up with 1/4 of the total minus the bits that aren't included when you get A, and so on. So you can see how it makes sense. And I think sort of thinking through a numerical example can sometimes help make it a little more concrete and what's going on. Okay, so let's now do a sort of a bigger example. And this also demonstrates why the constraint approach is actually useful. So GDP, this can be computed in several different ways. So one of those ways takes income and looks at how income can be used, in different types of income can be used to construct a GDP. And so here is a simplified version of how to do that. Or it can be done using expenditure. So here's a simplified example of how to do that. Both of these things should give you GDP. But of course, there's different series here at the, in the tree. And so when you add up all of these things, you're going to get a different estimate of GDP than if you do it using this set of series. Of course, the country only wants one estimate of GDP, so we're going to have to do some combination here. And each of these can be subdivided further. So this purple one, gross fixed capital formation, is computed like this, and then the other one is computed like this. So there's lots and lots of series that need to be combined here. So there's not a unique hierarchy. You can do it in several ways. I've showed you two, the income and the expenditure way. But they're meant to add up to the same thing. They're meant to add up to GDP. In the original notation that I talked about last time, the structural or the summing matrix notation, it's actually not possible to represent both of these things in the same summing matrix. You have to end up with two different summing matrices. But if we use the constraint notation, you can actually write it down, and it works. So you can apply forecast reconciliation to this problem and you'll get one estimate of GDP if you use the constraint notation. If you use the structural notation, the summing matrix notation, you can't do that. So here's how you would do it using the structural notation. So we have X as the GDP, the thing we're trying to estimate. A is a bunch of aggregated series and B is a bunch of bottom level income series. And then you can do the same for the expenditure. You've got GDP, the same GDP at the top, but different aggregated expenditure series and different bottom level expenditure series. And so the summing matrix for the income, the one with the I superscript, is like this, and the summing matrix for the expenditure with the E superscript is like this. And you can reconcile them individually, but you won't get the same GDP. If we use the constraint notation, all we have to do is to put all of the different things into the big Y matrix, the GDP at the top, all of the income series, whether they're aggregated or bottom level, all of the expenditure series, and then you just set up the C matrix to combine them all together. And so you can actually do this. So again, another paper by Tommy D'Afonso and Daniela, who's PhD student, and Luisa Bisaglia, a colleague at the University of Padua, did this. Sorry, went backwards. So that sort of demonstrates why the constraint notation is better, because you can do more things with it than you can with the structural notation. Not only is it computationally efficient, it allows you to solve problems that you can't solve the other way. Okay, so next I want to talk a little bit about the geometry of the problem, how this works sort of in a geometric sense. So it'll be a little bit of a geometry lesson, but also a little bit of a recap on linear algebra. So yeah, it's hard to do pictures in 4 or higher dimensions. So I'm going to have to make my example even simpler for the picture and just have 2 bottom level series and 1 at the top. So you've got a total and you've got an A and a B. And then you can draw it as this 3D image. And remember, A plus B has to equal the total. So everything has to lie on a plane. You can't have points lying off this plane because then they're not going to add up together. So we call this plane the coherent subspace, and all of the data should lie on this plane here, so that A plus B is equal to the total. And in general, thinking beyond this little 3-dimensional example, in general, you've got a large space of time series, but there's a subspace within that where everything adds up, and we call that the coherent subspace. The time series must live on that by definition. Sometimes there might be measurement error, so it doesn't exactly live on that, but conceptually you want things to add up. And so you say something is coherent if it lives on this space. So your forecasts are coherent if they live on this space. In general, your base forecasts are not coherent. You forecast from all the different levels and they're going to live somewhere that's off this plane. because they're not going to add up properly. And what we're doing when we're doing reconciliation is mapping things from off the plane onto the plane. We're taking the base forecasts which live sort of not sitting on this space, and we're mapping them onto it. So the idea is we have this some kind of mapping function that takes it from off the space onto the space. Now, if you've done linear algebra as an undergraduate or a postgraduate, you will know that mapping things onto a space, one way to do that is called projections. So there's a lot of projection theory that is involved here in forecast reconciliation. Before I just talk about that though, let me point out that this S matrix that I've been using is, there's not only one way to do that. There's actually lots of ways to do that. And again, I'm going to use a little example to show you that why it doesn't really matter what it looks like as long as it spans the right space. So that's how I did it originally. I said you've got a bottom level series of A, B, and C. We add them up to get the total, and we take the identity. So that's one way to do it, one way to construct an S matrix. But we could actually leave out the C series and take the total, the B series, and the A series, and make that our bottom level. And then our total is just 1 times of the total times 0 and 0. Our A series is just the last one. Our B series is just the second one. And our C series is the total minus B minus A. And that gives us an equally valid way to write down this summing matrix. And once you see that, you realize that there's actually an infinite number of ways you could write this down. The important thing is, so there's another one. I could write it down as the total and then the sum of B and A and the sum of C and B, and I can figure out how to, from these 3 series, how to construct the ones we're interested in. So all we need is to have the S matrix span the coherent space, and then we're good. Okay, so that sort of introduces the idea that this S matrix has to consist of columns that span the space we're interested in. Now let's talk about projections. So projection you can think of as a shadow. So if the sun's here and we're projecting from this line, this blue line, onto this red line, then the shadow falls like that. And so that's a projection of blue onto red. Thinking about it in high dimensions, here's my data, and I can project them onto the span of these 2 series. So if this is volume and this is girth and this is height, then I can project down onto that space. So it's like a shadow if the sun's sitting at the top. Or I could project them onto a plane. So if this is my plane, I can project onto the plane by, again, shadowing onto it like that. Or I can, if my sun's over here, I can shadow in a different direction. So you can think of projections as like shadows where the light source is from some angle and you're projecting onto some plane. So now a little bit of algebra. So a projection is any linear transformation M where M squared is equal to M. So M is the matrix that maps your original points onto where you're trying to get them. And M squared must equal M to be a projection. It's idempotent, which just means that if something already lies on the space, then it stays on the space. So the projection of a point that is already coherent stays coherent. So another way to say that, if Y is on S, then My is equal to Y. Another property of projections is that all the eigenvalues are either 0 or 1, and that all of the singular values of M are greater than or equal to 1. If it's an orthogonal projection, that means it's at right angles, then the singular values are all equal to 1. It is an orthogonal projection if it's symmetric, so M prime is equal to M, and it's not just symmetric, but if M prime is equal to M, and if it's not orthogonal, it's called an oblique projection, so at an angle. So that's sort of very quick view of what projections are. You've all used projections, even if you've never studied linear algebra, because in regression, ordinary least squares is an orthogonal projection onto the space spanned by the predictors. So when you're fitting a regression model, you're actually doing an orthogonal projection. Okay, so let's go back to the diagram. So if I'm projecting these points, these grey points, so if I've got these grey points and here's my space, the S vector here, this black line, and there's my point forecast, which is not on the space, then if I project all of these points, I'm project orthogonally, I'm going in this direction. So going directly down onto the S. So notice that these are right angles. So that's a right angle there. So that's called an orthogonal projection, and it gives you the smallest possible adjustments. An oblique projection goes in this direction, or some other direction, but in this case, I'm going in the same direction as the points lie, and that gives me the smallest variance. So that's what MINT was doing. It was projecting like this, down in this way, instead of like this orthogonally down in this way, which is OLS. Okay, so now that we've sort of seen that reconciliation is all about projections, we can then use some of the properties of projections to derive things about forecast reconciliation. So at the top, I've got a general expression for my reconciled forecasts as a matrix M times my base forecast. And if it's a projection, then I can, if M is a projection matrix, then I can immediately say things about what these forecasts look like. For a start, it means that coherent forecasts stay there, they don't move. So if they already are coherent, whatever you do is not going to change them. If my original forecast, these y hats, are unbiased, then my new ones will also be unbiased, and it's very easy to prove that. So the expectation of your reconciled forecast is just going to be the expectation of M times the base forecast. The M's a matrix, so it comes out the front. It's a deterministic matrix. So you've got M times the expected value of y hat, and they must lie on the subspace, because in expectation it's unbiased. So in expectation, that's going to be the same as the expectation of the data. So that has to lie on the subspace. And because M is a projection matrix, therefore it equals the expectation of y hat. And that's it. Like, that's the proof to show that if you're doing projections, unbiasedness is preserved. The last result I just wanted to point out is that if the S matrix forms a basis set, then projection matrices always look like this for some positive definite matrix. And again, you should recognize that, because that's actually that looks like the MINT solution with a particular type of psi matrix. So you get a lot. Once you realize that we're doing projections, you get a lot of value by applying projection theory. Let's do a little bit more. So again, I'm putting at the top here the general expression. Y tilde is equal to M times Y hat. I now know from the previous slide that M must look like this. I need to choose the psi matrix. If I choose it to be the identity, I get an ordinary least squares projection, which earlier in the week I wrote like this. Now I can write it like this using our new notation. The MINT solution, if I just make the psi matrix equal to WH, then the MINT solution looks like this or like this. I can write down the variance. The variance of my reconciled forecast is going to be M times WH times M prime, simply just by applying the variance to this term here at the top. And that's going to be minimized when the psi matrix is equal to WH, which of course is the MINT solution. So yeah, once you realize we're in projection space, some of these things just fall out. Okay, we can do a lot more though. There's all sorts of other nice mathematical results to do with projections that we can apply now to to forecast reconciliation and derive some really interesting and quite cool results. So here's one. So this, I'm putting at the top here the paper that this first appeared in, or where the result comes from. So you can see that this comes from a paper by Anastasios Panagiotellus and others, including me and George, and our PhD student Pawasala Gamakamara. So Hyndman's not a particularly short name, but it's almost always the shortest of the co-authors in this literature, because I write with Greeks and Sri Lankans. So here's this result. So here's a distance measure. So for a particular covariance or particular positive definite matrix psi, then that gives me a projection, and then this gives me a distance. So the distance between points on this in using this particular projection. And this result says that the distance between my reconciled forecast and the actual values is always less than the distance between my base forecast and actual values. So projections are always going to give you better, more accurate results, not just in expectation, in actual distance using this measure. So you're guaranteed to improve forecast accuracy by this distance measure. It doesn't mean that every single forecast is going to get better, but the total distance is going to get better by this distance measure. For any realization in any forecast, it's quite an amazing result. And it means that if we're doing ordinary least squares reconciliation, the distance between the forecasts and the actuals using Euclidean distance will always be improved by doing reconciliation. It doesn't mean that other measures of forecast accuracy are going to also improve just by this measure, by this distance, but still, it's a pretty amazing result. Here's another one. This comes from a paper by Shonika Wickramasuriya, and this is that the distance, the L2 distance between the reconciled forecast and the actual is always less than, less than, there we go, I do have a less than sign, always less than the distance between the base forecast and the actual. So you're always going to reduce in this sense too. And every projection reconciliation is better than base forecast using this distance, which is Euclidean distance. So you get improved mean squared errors. Another result that Shonika proved was that the trace of the covariance matrix for MINT is better than the trace of the covariance matrix for OLS, which is better than the trace of the covariance matrix for the base forecast. So your MINT reconciliation is better than OLS, and OLS is better than base. Always. And quite a remarkable result. And all of this just comes out through, thinking about reconciliation as projections and then using the results of projection matrices. Okay, so let me now look at optimization. I see someone's got their hand up. Let me just... I thought they did. Must have put it down again. Let's go to optimization. So when this is from last week, last lecture. So minimum trace reconciliation is the where we minimize the trace of the covariance matrix. So you minimize the sum of the variances. So it's L2 optimal. It solves an optimization problem, and it's given by this expression. There's a bunch of other optimization results that are worth pointing out here. So one of them, coming from this paper by Van Erven and Cugliari in 2015, showed that you get the same result, the same MINT solution, by solving this minimax problem, where you're trying to sort of minimize the worst case scenario. So the loss function, it can be any loss function, so this is the distance between your actuals and your base forecast. This is the distance between your actuals and your reconciled forecast. And you're looking at the worst case actuals So that's what this maximum over y is. And you're looking at the smallest of those. So you as close as possible to the base. So that gives you this minimization over y tilde. And they showed that this leads to the same solution, which means reconciliation is guaranteed to reduce your loss function. Again, a pretty cool result. Another optimization approach, which I just want to point out in passing, is this one by Sawai Ben Taeb and Bonsu Ku, who said, well, why do we impose unbiasedness? Let's see if we can find the best forecasts through mean squared error, but not necessarily making them unbiased. And so they derived the best forecasts for this problem, where you set it up as this optimization. So you're looking at the Frobenius norm here over y. So y is your original your actuals, and y hat is the base forecasting. You're trying to find the best G to do this. And they showed that the best G was given by this expression down here, where B is the base observations. Somewhat limited result. Sort of, it was cool, but somewhat limited because the theory assumes that all the series are stationary, which is almost never true. So there's some space there for some people to extend this, I think. And you can also do it as a regression. So since the MINT solution gives you this expression, and that looks a bit like a regression solution, you can actually write it down as a regression problem. So your reconciled forecasts at the bottom level can be found using this optimization, which is a regression optimization. And it's very easy to show that that leads to this result, because I just rearrange it and it turns out that I'm trying to solve this problem. And if I replace that B by this guy up here, then this becomes 0. What I've got on this bottom line becomes 0, because both terms are going to be equal. And that's obviously the minimum, because the result has to be non-negative. So the MINT solution is equivalent to GLS regression. So you can demonstrate that in just 3 lines. So it gives you another perspective on it. Another way of thinking about it is, because we're solving this optimization problem, this one here, that's the one that led to the MINT solution, we can do a constrained optimization and say, well, we want that solution, but we want it in such a way that all of our forecasts are non-negative. That has practical implications, because often when you're doing forecasting, the things that you're forecasting must be non-negative. Imagine forecasting sales or demand, it can't be negative, so you want them to be always non-negative. So it's a constrained optimization problem then, and that can be solved using a quadratic programming solution. So the constraint means you can't apply MINT directly, you have to apply it using quadratic programming, but it's possible to do. And that slows things down a lot, of course, because it's now iterative. You can't just write down the solution. But it turns out that there is an approximate solution which is extremely fast, and that's one that Tommy and Daniela came up with this year, or published this year, and that is, do the MINT thing, and then you take any of the bottom level series, the reconciled forecasts that happen to be negative, and set them to 0, and then just add up. So extremely fast to compute. You just set all the negative ones to 0 and aggregate, and you'll get something that's close to optimal. It won't quite be as good as the solution via quadratic programming, but it'll be much, much faster to do. And then wanted to point out one other constrained optimization that people have done, which is immutable forecast. I'm not going to go through the maths here because I want to leave a bit more time for questions, but immutable forecast says, well, instead of requiring all of the forecasts to be non-negative, you might require some of the forecasts not to change. So you do all your base forecasts, And when you do the reconciliation, you want to fix some of them and say, well, don't change those ones, reconcile the other ones to make, but leave that one the same. Now, a example where you might want to do this is where the total has to be fixed. So you might be using your forecast to allocate budget, and you're allocating certain resources based on projected activity in different spaces in the company. But you can't change the total budget. Like, you've only got so much money. So you want to keep the total forecast fixed, but you want to reconcile the others so that they add up to your total. And that would be an immutable forecast where you fix something. And so the certain series get fixed. And in this notation, they're the U's, this collection that I've put at the bottom. The V's are things that can move that are bottom level, and the A's are aggregations that can also move. And then you can solve this using an optimization problem. It turns out you can solve it using the same non-negativity approach, just by rewriting it. Again, I'm not going to go through the maths, but it's in a paper by Zhang et al. I think it was the Journal of the Operation and Research Society. Another perspective. So again, I'm just running through lots of different papers that think about this problem and sort of pointing out different perspectives. So this one said, well, instead of doing a second step reconciliation where you forecast stuff and then reconcile them, you could try to build it in to the original forecasting process. So you can say, well, I want to find the best forecast. So that's the usual. This bit is usually what you're doing when you're forecasting, is you're trying to find the best forecast, the closest in L2, minimum mean squared error forecasts. And they said, well, do that, but just impose this constraint or this penalty where your forecasts have to, you look at the difference between the forecasts and the S times B hat, which is what you would get if you added up the bottom level. And so the difference, this difference is going to be your reconciliation error, and you just penalize based on that. So for a large enough lambda, you're going to get things that are pretty close to coherent. So this works well if you can build the penalty directly into your calculation of the forecast. So for example, if you're doing neural nets, you're generally trying to solve something that looks a bit like this. And so you can add in a penalty and you get not coherent forecast, but close to coherent forecast, depending on the value of lambda. And then a bit later, a year later, these Japanese machine learning researchers came up with a more efficient way to do it. And they said, well, you don't really need to do the whole matrix, like the whole vector here. You can just do the bottom level, the B hats, but your penalty includes the aggregation series. And you want those to be close to what you think they should be. This is a more computationally efficient way to do built-in regularization to get something close to coherent. Disadvantage of this is they're not, unless lambda's huge, they're not actually coherent, they're just close to. There are a couple of methods that really do lead to coherence in one step. I'm just going to point out three of them. So remember, the way I've been talking about reconciliation has been a two-step process where you compute lots of base forecasts and then reconcile them. One-step processes are where you're supposed to compute the forecasts that are already coherent from the start. And there's three papers I know of that do this. One with Masa Ashuri and me and Galit Shmoili, which I'll show you how that works, and then two that use state space models. So let me do the regression one first. So turns out that if you can write your base forecasts using a regression model, so like this, so this is just a regression model for base forecasts, whatever X is your predictors, Y hats your forecasts, beta hats your coefficients, then so your forecast, your base forecast can be just written like regression. If you can do that, then your B hats, which are your coefficients, look like that. So your Y hats look like that. And where your X matrix here is the futures. Then you can write your Y tilde, because this is just a linear function. You can write your Y tilde using this big long expression, but that's one line. So you do it in one step. You just it's like a regression, except instead of the matrix at the front being this little guy, which is what you'd normally do for regression, you end up using this great big expression here. But in one step, you can do reconciled forecasts. It requires, of course, that you can use regression to do it and not some other model. The state space approaches try to build a coherence in by putting the summing matrix here, and this mu term is written as a multivariate random walk. And if you can write your model like that, then you can do coherence directly. There's a couple of problems with this approach, though, that I see. One is that not all models can be written like this. And secondly, these covariance matrices here are really hard to estimate, almost impossible to estimate. And so it really doesn't work particularly well unless you've got quite small numbers of series. But it's sort of an interesting way of thinking about it. So that was the Pennings and Dalen one. A quite similar one is done by Villegas and Pedregal a year later. And then the last thing I wanted to talk about was I wanted to talk a little bit about time series cross-validation in the reconciliation setting, and show how that can lead to another way to do reconciliation. So just to remind you, in case you don't know about time series cross-validation, let me just briefly explain the idea. So normally what I did last time actually was we had a set of training data, and I kept back, so it's my training data, I kept back some data, which were the test data. I fitted a model to the training data, I predicted the test data, and I evaluated how good my model was by how well it predicted the test data. In time series cross-validation, you do the same thing, but you do it with lots of different training sets, and those training sets grow sequentially. So you start off with this training set and you forecast the next observation. And then you increase your training set by 1 and you forecast the next observation, and so on. And so you end up with lots of forecasts for one step ahead based on increasingly large training sets. And I can do it for 2 steps ahead and 3 steps and 4 steps and so on. And your forecast accuracy is then averaged over the test sets. So I call this time series cross-validation. Sometimes it's known as evaluation on a rolling forecast origin. So let's do that on the tourism data, just to see it in action, and then how you might use this to improve your reconciliations. So remember the tourism data. We had tourism in Australia split by state, zone, and region. And I can construct aggregates like this. So this was from last time. I just constructed all my aggregate series. What I'm going to do new here is to then construct lots of different test series in this second step called tourism stretch. So I'm going to construct lots of training sets, increasingly large. The initial one is going to be 48 observations long, and then all of the subsequent ones will just be one bigger than the previous one. So I now get an enormous, there's 3 million rows here because I've got lots and lots of training sets. I fit ETS models to all of the different training sets. There's 21,230 models. And I reconcile across all of them. So I get an enormous number of forecasts, and then I look at how well these did for different horizons. So the original forecasts are in the orange color, and then all of the others are below. So you can see that you can see the ETS, if you look closely, the ETS is the top one, and then all of the others are less. So the reconciliation is always improving. And the one at the bottom, that is the one that's the best, is either the blue or the green. If I just summarize overall, you can see that on root mean squared scaled error, minimum trace and OLS are pretty much the same, followed by the other two, and they're all better than the original series. If I do it by national level, state level, zone level, or regional level, you can see again that the two that are the best of these two, and they will almost always give you better results. So that confirms what we did last time, but last time we did it on a test set and a training set. This time we've done it on a cross-validation procedure. Okay, so the last thing I want to say is how you might use that idea to do reconciliation. So this comes from a paper in Applied Soft Computing from 2 years ago by Spiliotis and a few others, including me. The idea is you split all the series using that time series cross-validation, and for each training set, you compute all your forecasts one step ahead. But then, rather than using Mint or anything, what we're going to do is to train a model to predict the bottom level series using all of the forecasts from all of the other series. So for every bottom level series, we're going to use either a random forest, that's RF, or XGBoost, that's XGB, to predict the values using all of the forecasts as the inputs to it. And then once we've got once we've built that model, we can then use the model to apply it to our bottom level forecast to improve the forecast overall. So graphically, what's going on is suppose I had this little simple set, then I do this rolling origin, I get lots of forecasts for each of them, and I can then build training samples for my machine learning models, the random forest or the XGBoost, and then I know how to forecast bottom level series using all of the forecasts, and I can do that and end up with forecasts that are therefore reconciled. And this turns out to work pretty well. So in the same tourism data, here is the couple of Mint methods, Mint structural method and Mint shrink method. And here's my two machine learning methods. And in general, you can see that the results, generally the machine learning methods are doing slightly better here. They're not significantly different from each other. Random forest and XGBoost are similar. The Mint methods are significantly different from each other, and they're significantly different from the machine learning methods. So the machine learning methods are significantly better than Mint for this example. We don't have all the nice theory to say, this is always going to work, as unlike for the Mint stuff, but it does work better here. And you might say, well, why does it work better when Mint's supposed to be optimal? Well, this is a non-linear reconciliation. Okay, Mint is optimal amongst all linear reconciliations. We know it's going to be the best. But it's not necessarily optimal amongst all possible reconciliations. And this is a non-linear reconciliation because we're building a machine learning model to do the reconciliation. And it works out it's slightly better here. Okay, let me stop there. I have a bunch of papers at the end of my slides with some of the references, the main references that I've talked about. So I won't go through them all, but if you want them, they're there. I'm going to stop there and have time for some questions. Okay, so I'm just going to read them off the Q&A or the chat, whichever one of those you wish to use. I've got them both open in front of me. So Russ Conter's asking, time series cross-validation takes longer than doing individual models. What is the runtime for all these models? I think it would be a very long runtime. Yeah, of course. I'm fitting lots of models here, like there was 21,000 ETS models. So yeah, if you're running on a single core on a single computer, then that's going to take a lot of time. They're ETS models, so they're fast to do. So it's not going to be days, but it's probably going to be, at least an hour, a couple of hours or maybe more. But it's entirely parallelizable. So you can run them all on multiple cores. So all of the different all of the different series, plus all of the different training sets, you can send out to lots of cores. So if you've got a big enough cloud computing infrastructure, then it can be done relatively quickly. Which reminds me, there was a question last time that I couldn't answer, or I wasn't sure of the answer, which was about how does Fable do parallelization? So Savandi was asking that question. And I checked, and it was what I thought, but I wanted to confirm it, that it'll do it by sending the each series to different processes. Okay, so remember in Fable, you're fitting, you give it a model statement, and it gets applied to all of the series in the object. So each of those series will go off to different cores. So the parallelization works on a series by series basis. Unlike the forecast package, because that only does one series at a time, the parallelization works on a model by model basis. Anyone else got a question? So does Fable do parallelization automatically? Do I have to use special code? So it's not automatic. You have to set it up using a plan. There's a vignette, I think, that shows how to do it, or maybe it's a blog post. But if you do a search on Fable parallel forecasting, you should be able to find it. And it uses the future package to set it up. So you have to sort of set up a plan and then run it, and it'll then do it. It's only one extra line in your code, so it's pretty simple, but you do have to run that line, otherwise it won't be doing it parallel. Okay, if there's no other questions, let me just briefly explain what's going to happen next, or feel free to write more questions. So what we've done this week is point forecasting. So I'm only worried about, getting the point forecast out. And we introduced mint forecasting, which is optimal, and then lots of different ways of thinking about it, or tweaks on that, or different optimization functions and how you would think about it. What we're going to do next week is two other things: probabilistic approach. So we're not just interested in the one number forecast, you're interested in the whole distribution. I'll do that in the first lecture next week. And then the second one I'm going to talk about is how to do temporal reconciliation as well as cross-sectional. So far I've only done cross-sectional, where you're trying to reconcile a cross series. So this series has to add up to these other series. But you can do it in a temporal direction, where you want to say my annual forecast should be the sum of my monthly forecasts, and they should be the sum of my daily forecasts, for example. So that's temporal reconciliation. And you do them both across series and across time. We call that cross-temporal. So I'm going to do that in the fourth lecture in the series. Okay, so Cheng is asking, suppose I use OLS to reconcile. The distance is reduced, but the YT consists of both aggregate and disaggregates, and the weight for the aggregate seems the same as the other subseries. Is it good to compare it this way empirically? So yeah, that's a good point. That any of these distance measures, you got to think about, does it make sense for the problem? And OLS is treating all of the series equally, and then looking at the distances. Now, the distance between the totals is going to be larger than the distance between the bottom level series, because they're going to be smaller numbers. And it may not make sense to think about it empirically in that way. Whereas if you use a covariance related distance, like we use in the mint solution, then you're scaling each of the series by the variances. So you're getting something that maybe makes more sense, but it might make more sense to only look at the distance between some of the series, the ones that matter the most, and not worry about the other series. Or it might make sense to have a loss function that's about the cost to the company and not about forecast accuracy at all. So there's certainly you need to think about distance and what makes most sense for the problem at hand. Imran's asking, is it possible to assign different weights to each subseries in the summing matrix? Sure. The summing matrix can contain any real values. So if you can write down your total as a weighted sum of some things, then sure, you can do that. The way the software is set up at the moment, it doesn't allow for that. It only allows for direct aggregations, but mathematically, there's no reason at all why you can't use, linear combinations here. You would just have to be able to write down you'd have to write your own code to do the reconciliation.
There's another question in the chat, in the Q&A.
Oh, yeah. So were there any considerations for using random forest to predict time series? I'm not sure what that means. My understanding is that random forest uses bagging. Wouldn't time dependency of the data be broken in this way? So we're not using random forest to predict the series, the base forecast. We're using random forest to take all of the base forecasts and to map them onto the bottom level. So I don't think time dependency matters there.
There's another question above that one, Rob, by Sebastian.
Oh, sorry, I missed that one.
Yeah.
How could one reconcile ensemble forecasts and forecast combinations? Okay, if we're talking about point forecast, it works exactly as we've just done it. So your base forecast would be the obtained from the ensemble. So it doesn't really matter where those base forecasts come from, those Y hats. They can come from anywhere. And if they come from an ensemble, you can take them and then reconcile them. So that should work just fine. Okay, looks like we've exhausted the questions, and we've exhausted our time. So why don't we leave it there?
Yeah, thank you, Rob. So for everybody else, we're going to meet next Tuesday if you're in the US, or Wednesday in Australia.
No, Monday.
Monday. Yeah, Monday. Okay.
Monday in the US and Europe, Tuesday in Australia.
Good. All right. Thank you. Thank you. So I'll see you in a few days. Okay. Thank you, Rob. And thank you, George.
Thanks, Rob.